Thank you, Torrin, for the invitation as well. Yeah, I'm excited to be here. My PhD advisor, Scott Holland, actually did his PhD here under Manny Parzan in, I think, 2004. So it's nice to be here and see where he spent a lot of his time. Uh, Also, I don't know if you know this, but Santa Cruz is typically not a hot place, but there's a heat wave there right now, and it was over 100 degrees right before I left. So I can actually say I came down to Texas to cool off, so that's nice as well. So this is joint work with Sho Kawano and Ziheng Li. Um, Sho is a PhD student at Santa Cruz that's jointly advised by me and Richard Lee. So brief outline here. I'm going to talk a little bit about some background of the type of data that I'm dealing with here, survey data. And then I'll talk about this general class of models, area level models for small area estimation, um, and some challenges there. And then I'll talk about our model that we developed, this spatially selected and dependent random effects, or SSD model. And then I'll highlight um, how we show how this model can perform with this empirical simulation study. And then before wrapping up, I'll talk about an analysis that we do to estimate rent burden at the county level. So I work a lot with complex survey data. So very often, federal statistical agencies like the U.S. Census Bureau will conduct these complex surveys. These are important for a variety of reasons, but generally, to sum it up, they are how we learn about our population. So we're estimating population quantities with these things. So one very important survey is the American Community Survey, or the ACS. So this is a survey conducted by the U.S. Census Bureau, and it has a large sample size. They sample about 3.5 million households every year, about 4.5 million people. So very big survey. They use this survey to supplement the decennial census. So the decennial census happens every 10 years, but the American Community Survey happens every year. So it helps supplement that. They also ask a lot more questions on more topics in the American Community Survey than they would in the decennial census. So you get information on other topics as well. Um, but this is a complex survey, meaning different individuals or different households are selected with different probabilities. And so it's important to consider that when we're constructing any estimates so we don't end up with biased estimates. So a little bit of notation here. Say we have some population enumerated by J here, J from 1 to n, and our population size. If we're interested in estimating something like a population mean, say theta here, that's just 1 over n times the sum of all the y's um, in the population, right? If we had observations for the whole population, we could just calculate that immediately. There's nothing to really do there. But we don't. We typically have a survey, so only a subset of the population. And again, these people are sampled with different probabilities. So very often, these design-based or direct estimates are used, something like the Horvitz-Thompson estimator given here, theta hat. So it's 1 over n times the sum. And this is a weighted sum for observations just in the sample. The sample's S here. So we see these observations, Y, are weighted by 1 over pi. These are the probabilities of selection for the sample. Um, so these direct estimates, things like the Horvitz-Thompson estimator, can be great. They have a lot of nice properties. They're unbiased. They're consistent. So we like to use these when possible. And they work very well when we have a large sample size, something like a population total or population average, maybe the average poverty rate across the US. It could work well in that sense. Um, where it doesn't really work well is when we have limited sample size. And so when we start to create estimates for subpopulations, maybe geographic areas like counties or census tracts, a lot of times these will have very small sample sizes, and these estimates can have large variance. They're not very reliable estimates. And so that's where models come into play. So there's a field called small area estimation. I work a lot here. And generally the goal is we want to use a model to estimate those population characteristics, those thetas, for different subpopulations. So often these are geographic subpopulations, so counties, census tracts, or they could be um, demographic cross classifications or some combination of these things. But these populations where we have a small sample size. And so small in smaller estimation refers to small sample size. And we do this with these complex survey data. So there's two general approaches to smaller estimation. So one class of models is area level models. And so here we're taking those direct estimates, like those Horvitz-Thompson estimators, and we're treating those as the response variable. So the Census Bureau releases a lot of direct estimates, and you can take these and model them. And so your model usually incorporates some smoothing, maybe through dependence structures like spatial dependence, maybe through covariates, or combinations of these things. And because the Census Bureau releases these direct estimates, these types of models are generally available to any analyst. You don't have to be necessarily within a statistical agency. You have access to those direct estimates. You can fit these types of models. The alternative would be a unit level model, where instead of working with those direct estimates, we're working with the individual survey responses directly. And the general idea there is you can fit a model with your sample data. You can get predictions for the entire population, kind of essentially creating a synthetic population and then aggregate it up to whatever level you want to create estimates at. But here you would need the individual data points. Often these are confidential microdata. So unless you're within a statistical agency, you might not have access to that data. So I think both classes of models are useful. I work on both. I'm not going to advocate for one or the other here, but I am going to talk about area level modeling specifically in this work. Um, I want to highlight a little bit further the importance of smaller estimation and official statistics in general. Um, so just with this one survey, the American Community Survey, here's a couple really important applications that come out of this survey. So one is poverty estimation. So there's a program called the Small Area Income and Poverty Estimates Program, or SAPE. And so their goal is to estimate income and poverty, like it says, by county and some other geographic regions across the entire US. And very similarly, there's the health insurance estimates, or the Small Area Health Insurance Estimates Program, or SAHE, where the goal is to estimate health insurance rates for these regions as well. And so these two programs here are used by the federal government to allocate billions of dollars in federal aid every year. So you can think of like targeted interventions, putting resources towards poverty and health insurance where it's most needed. And so these are very important estimates that come out of small area estimation models. Another really important program is language minority estimation. So basically estimating the number of language minorities in different regions. And so this is related to this Section 203 of the Voting Rights Act. Basically, certain regions that meet certain classifications are required to receive registration and voting assistance. So it's very important in that context as well. And this is just with this one survey. So these are very important problems. It is very worthwhile to create new small area estimation methodologies that can better predict population quantities like these or other things. All right, so as I said, I'm going to talk about area level modeling here. And this is what's called the Fay-Harriott model. And it's kind of the foundational area level model. Almost all area level models used nowadays are built upon this model. And so here, this y, indexed by I is an area. Y is assumed to be normally distributed around theta, and theta is our true population quantity, the thing we actually care about. So y is a direct estimate, like a Horvitz-Thompson estimator. It's normally distributed around theta. And then the variance is this d sub I. And so that's the design-based variance of y. So when we construct a direct estimate, we can also estimate the variance of that direct estimator, and that's d. Now this theta, this true population quantity that we're interested in, is further modeled here as a linear combination of some covariates x, these are area level covariates, plus some random effect. And they assume this IID normal random effect structure. And so the things in red here are basically the inputs into the model. So we need our direct estimates y, we need their sampling variances d, and we need whatever covariates we're interested in using x. That's our data. So if you write out the empirical best linear unbiased predictor of theta under this model, this is what it looks like. And so you can see it's the sum of these two terms. The first term includes y. Y is our direct estimate. And the second term includes this x beta. So you can think of that as like a regression estimate. So these are both estimators of theta. One's a direct estimate, one's a regression estimate. And if you look at what happens when d gets small, that means that y, our direct estimate, is it's a good estimate. It's precise, it has low variance. And so when d is small, y is given more weight. We give more weight to our direct estimate. When d is large, that means our direct estimate is not reliable, it has a large variance, and we see that this regression estimate gets more weight. And so this is a nice property because we like the properties of our design-based estimator, our direct estimator, when the sample size is large or when the variance is small. And so we're giving more weight to that when that occurs. You can also assess this visually, which I'll show an example of later. So here I'm just rewriting that Fay-Harriot model in matrix form. So our vector of responses, y now, is now multivariate normal around this vector theta, and D is a diagonal matrix of those variance terms. X is just going to be an n by j covariate matrix here. And so, again, this is the foundational area level model. A lot of work builds on this, and a lot of work is kind of built around some criticisms of the random effect structure here. And so the Fay-Harriot model assumes an IID normal random effect structure. But there's two kind of criticisms of this that I want to talk about here. And so the first is that the model doesn't account for any spatial dependence. So if you just took some direct estimates for something you were interested in, like poverty rate, and you made a map, you plotted them, you'd probably see there's some spatial structure there. And so we might want to account for that spatial structure in our model. We might want to make this random effect spatially dependent. So that's one criticism. There's a lot of work that has done that. And then another criticism that's a little more recent is that not all random effects may be necessary in the model. So it turns out if you don't include some random effects, or maybe you don't include any random effects, you can get better estimates of these population quantities. So I'm going to talk a little bit more about these two assumptions, and this is kind of the motivation for our work as well. So first, talking about spatial dependence. As an alternative to that IID normal assumption, we could make our random effects have some spatial structure, right? So we could say instead, mu is going to follow a multivariate normal distribution with this sigma squared times Qn versus our covariance matrix, where now Q is just some spatially structured precision matrix. So very often, this matrix Q will take the form of a conditional autoregressive or CAR model. So in this case, Q is going to be diagonal matrix with elements n sub I minus rho times the matrix A. And so this matrix A is going to be a spatial adjacency matrix. So Aij is equal to 1 if areas I and j are neighbors. So we can denote that as I tilde j. If they're not neighbors, then Aij is 0. By neighbors, we often mean that they share a border. That's one example of spatial neighbors that you could consider. So this is our matrix A, and then n sub I is just the number of areas, or the number of neighbors the area I has. And so we could actually look at the conditional distribution here. So mu sub I, the random effect for area I, given all of the other random effects. So mu sub minus I, and we see that this is going to be a normal conditional distribution where the mean is a weighted average of its neighbors. So I tilde j. So it's a weighted average of its neighbors. So if one area has neighbors that tend to be above average, this area will probably also tend to be above average and vice versa. Rho here is just a spatial dependence parameter. And so another commonly used prior here is setting rho equal to 1, and that results in what's called the intrinsic car or I-car prior. That's used as well. Now, one issue here is that it's been shown that if you use these car random effects when there's weak spatial dependence, that can lead to inefficient and misleading results. So a common alternative is to use this B-Sag-York-Molly prior or BYM prior. And so here we're taking the random effect mu and structuring it as the sum of two components, V1 and V2. And so V1 is an IID component, and V2 is an I-car component. And so here you can see as sigma squared 2 goes to 0 and sigma squared 1 does not, we basically get back the IID random effect. As sigma squared 1 goes to 0 and sigma squared 2 does not, we're essentially getting the I-car. And so we can get some balance between those two things, and that's nice as well. So these types of priors have been used in small error estimation. Yeah, is there a question? Yeah, so misleading, meaning you can basically infer that there's more spatial dependence than there actually is. Inefficient, meaning we can get more precise estimates if we use something like this. Yeah. So again, all of these spatial priors have been used in small error estimation. There's been plenty of work that has done that. The other criticism I want to talk about is that random effect inclusion. So a more recent line of work is basically detecting whether or not we need some or all of the random effects in the model. And this was kind of started by this Dada et al. Paper in 2011. And there they were looking at the problem with a hypothesis test. So they were basically considering, do we include no random effects or all of the random effects? And they found in many cases, not including any random effects can give better results. So that's interesting because it kind of sets the stage for this inclusion or not of random effects, but it's not really desirable because it's an all or nothing approach, right? We either have all of the random effects or none of them, and they're not really considering anything in between there. And so this follow-up paper in 2015, they instead use a spike and slab prior for those random effects. So here they're actually selecting which random effects are included or not included in the model, and that can differ by area. And there's been some other work along these lines, this Tang et al. Paper and Ghosh et al. Paper. They're doing kind of a similar thing. They're just using global local shrinkage priors rather than the spike and slab approach, but all very similar types of work. And so I want to look for a bit at this data and Mendel model, or DM model, I'm going to call it, where they're using that spike and slab prior to select the random effects. And so they write the random effect U for area I as the product of this indicator term delta, and then V, which is kind of the random effect component. And so when delta is 1, V is going to get this normal prior. And when delta is 0, V is going to be 0. So you can think about delta as an indicator of selection. If it's 1, the random effect is selected or included in the model. If it's 0, the random effect's not selected, it's not included. And these deltas vary across areas. And they're modeled as Bernoulli with probability P here. And P is a common probability across all areas here. And then they just put this beta prior on P. So that's the DM model. And so that brings us to our model. And our goal is to kind of address both of those criticisms of the random effects together, right? So we want to develop a model that allows for the selection of the random effects, but also while considering spatial dependence. So the work developed on selecting those random effects is kind of throwing out all of the nice work in small error estimation that considers spatial dependence. So we want to put those things together. And when we look at this DM model, we kind of think of it as these two different stages of these two different components. And so we have the random effects model, right? So modeling V here, maybe conditional on these indicators. That's one part of the model. And the other model is the selection process. How are these indicators themselves modeled? And so when we say we want to model spatial dependence, we actually want to do it at both of these levels. So you can think about our quantities theta are going to be spatially correlated, but also the idea of whether or not a random effect is included is also spatially correlated, right? An area that does not need a random effect is probably going to have nearby areas that also don't need a random effect or need a random effect with lower probability and vice versa. And so we want to incorporate spatial dependence at both of these levels. And so we developed this spatially selected independent random effects model, or SSD. This is an area level model. So the data stage here looks just like the Fay-Harriott model, right? It builds off of that. So y given theta is multivariate normal, mean theta, covariance matrix is thus diagonal matrix D. And again, theta is modeled as x beta plus our random effects mu. And then all of the development goes into this structure for mu here. And so again, if we first look at that random effects component, this is what that looks like for our model. So we say mu I is equal to delta I plus vi1 plus vi2. And so we're putting a BYM structure on the random effect conditional on delta equals 1 here. So we have V1 is the IID component, V2 is the spatial component. And this is our random effect structure. So very similar to the DM model, only we have a spatial structure here for these random effects. If we are putting spatial structure in that random effects stage, we also want to do that for the selection process, those deltas themselves. And so this is the model for that selection process. So we model these indicators delta now as independent Bernoulli with their own unique area level probabilities, P sub I now. And we model those probabilities on the logit scale again with that BYM structure. So we have psi1 and psi2, where again, psi1 is an IID component, psi2 is an ICAR spatial component. And so we're putting spatial structure into both the random effects stage and the selection process stage. And then the model's completed with our prior specification. So we put a conjugate normal prior on the regression coefficients beta. We put conjugate inverse gamma priors on all of the random effects variances, sigma squared 1, sigma squared 2 for the random effects, and S1 squared and S2 squared for the logit effects. And then we make some recommendations as well. So we recommend standardizing the data Y and the corresponding variances D, similar to what you might do in any other variable selection problem. We recommend scaling the ICAR precision matrix with this method in Sorbai and Roux so that the random effects variances are comparable. And then we recommend setting A and B in a way such that the slab is wide but without too much mass close to 0 so that we're not conflating the spike component and the slab component. We found for standardized data that I think inverse gamma 5.5 worked well for that standardized data. And then lastly, we just set sigma squared beta to be large, non-informative. And then for posterior inference, we were able to develop a Gibbs sampler. I don't want to dive too much into the details of this, but I'll highlight a couple important things. So first, we block our fixed and random effects. So we block beta, V1, and V2 together into this vector gamma. And this matrix Z is a block matrix with components X, and then delta and delta, where delta is a diagonal matrix of those inclusion indicators. And so then you can see that Z times gamma is the same as X beta plus our random effects, or the model that we wrote out earlier. And then our full conditional for gamma is multivariate normal, so we can draw from that. The full conditional for those indicators themselves, delta, is going to be Bernoulli with this probability p tilde given here. So again, pretty straightforward to sample from that. The only one that's a little bit tricky is those logit effects. They're not conjugate, but we're able to use polygamma data augmentation here. So essentially, we introduce these latent variables W for every area. And then the full conditionals for those W are going to be polygamma with these parameters 1 and then psi1 plus psi2. So we can update those in a straightforward manner. And then conditional on those, we're going to block our logit effect, again, psi1 and psi2. And the full conditional for that blocked logit effect will again be multivariate normal. So pretty straightforward to sample from that. And then all of our variance parameters are going to have inverse gamma flow conditionals. And so we're able to set up this Gibbs sampler. It's pretty efficient, scales decently well to fairly large data sets, like I'll show in the example towards the end. All right, so evaluating these small error estimation models is a little bit tricky. It doesn't really make sense for us to do something like cross-validation, right? Because that would be holding out the direct estimates. And our goal is not really to estimate the direct estimates, right? We already said they're not good estimators. We want to estimate theta, but we never actually observe theta. We never know what the truth is. And so we instead do what we call an empirical simulation study. Essentially, we're setting up a situation where we know the truth, we know the truth theta, but we only model some synthetic direct estimate. But we want to do this in a situation where the data, these synthetic direct estimates, are somewhat similar to like we might observe in a real data set. And then we can compare our estimates based on those fake direct estimates in our model to those known truths. And so the way we do this is we take some existing data set, right? We can take existing direct estimates from the American Community Survey, and we can just pretend that those direct estimates are our true population quantity that we'd like to estimate. And then we add some noise onto it. And we add noise similar to like we might see in the actual data. So in this case, we take our existing data, Z. Z is the direct estimates from the survey. D is its sample variances. In our case, we're working specifically in North Carolina for this simulation study. Our target variable is county level rent burden, median rent burden. So that's the median rent as a percentage of household income. And we're pretending that those direct estimates are our true values, and we're adding some noise. And we add noise according to the reported sampling variances, right? According to those Ds that were given in the data. And then these new noisy versions that we've created, we're treating those as our direct estimates. Right? We're going to estimate this underlying truth that we now know. And we do this a bunch of times for this simulation study. One note here is we're adding the noise on the log scale, and then we're actually transforming back to the original scale here. So this is what that North Carolina data looks like. So on the left, we just have a map of those original direct estimates. These are the direct estimates reported with or from the American Community Survey. And so you can see some spatial structure there. You can see they're a little bit higher in that, that eastern region. On the right, we also have a plot of the rent burden versus the log sampling variances. And then the top three in blue are just any that were over 0.4. I think it's those three red areas you see there. So essentially, these are the direct estimates on the left. That's what we're calling the truth. We're adding noise to that, and then using these noisy versions to estimate this, which we now know. Now, when federal agencies release estimates, they typically release a point estimate and either an interval or a standard error. And so when we construct our own estimates, we want to know how good is our point estimate and how good is our interval estimate. We're going to release both of those things. Um, so when we're evaluating our model, we want the model to have precise and accurate point estimates. That's one thing we'd like. And we also want short intervals that have the appropriate level of coverage. So when we're looking at these two, or when we're looking at our models, these are kind of the two things we care the most about here. So we're going to look at the average mean squared error. We like mean squared error because it balances bias and variance. So it's balancing precision and accuracy. That's how we're evaluating our point estimates. For our interval estimates, we're going to look at this interval score, average interval score. And again, this is kind of balancing interval length, right? So you're rewarded for small intervals, but you're penalized if you don't have the right level of coverage. And so again, it's balancing those two things. So this is the main criteria we're going to look at for our models. We also look at the average absolute bias and the average coverage rate, kind of components of these two other metrics. Okay, so we're going to obviously compare our model to some other models. First of all, we compare to the direct estimate itself, right? The direct estimate is the noisy thing we created. We're going to compare to that. And then we're going to compare to some other small error estimation models in the literature. So we're going to compare to the standard Fay-Harriott model that I presented earlier. We're going to compare to a spatial Fay-Harriott model that uses a BYM random effect. And so that's the model I'm just calling BYM here. We're going to compare to that DM model that has the inclusion indicators for those random effects. And then we'll have our model. And so the first thing we're going to look at here is the average mean squared error, MSE. You'll see it's very high for the direct estimate. That makes sense. We obviously don't expect the direct estimate to be a good estimator. Any model we come up with should beat this quite handily. And in fact, we see that all of the models do outperform the direct estimate by quite a bit. Then if you look within the four model-based approaches, you'll see that the SSD model outperforms the other three by a healthy margin. Coverage rate, so we're creating 90% prediction intervals here. You'll see that the SSD model is pretty much spot on here, right about 90%. The other three models have some degree of undercoverage. That's also partially reflected in the interval score, where again, we see the SSD model is outperforming the other models. And then if you look at absolute bias, the direct estimate is the best in this case, which makes sense. It's an unbiased estimator. It should have the lowest bias. In the other cases, we're imposing some model, so there's going to be some degree of bias. But within the four model-based approaches, the SSD model has the lowest absolute bias. And so that's comforting to see as well. And so we see that there's some evidence that this new SSD model can create better predictions, both in terms of point estimates and interval estimates compared to existing approaches. Yeah. Target's 90%. Yeah. Because the Census Bureau usually releases 90% intervals as well. So we're just kind of matching that. So here's a plot that's each frame is one of the estimators, not including ours. And then we compare the log MSE of that estimator on the y-axis versus the log MSE of our estimator on the x-axis. So again, us versus each of the other four approaches. And each of these points represents one of our simulated data sets, one of those noisy draws that we took. And so anything that falls above this line in blue is a case where our model outperformed the other approach. The distance from the line is basically how much better it was. Anything that falls below is a case where the other model did better, ours did worse. And we can see the vast majority of the points, regardless of the other model here, are above the line in blue. And so generally we're doing quite a bit better than the existing approaches. All right, I want to talk a little bit now about a data analysis that we did. So actually applying this model to a real survey problem. And so just like our simulation study, we're going to use median rent burden here, median household rent burden. That's the quantity of interest. We want to estimate median rent burden using those direct estimates. And this is a policy relevant variable here. And so recently, ACS estimates have shown that over half of US renters are paying more than 30% of their income in rent. And so this is a real issue. You might think about targeted interventions for rent burden being an important topic. It was especially important to my PhD student Show, who's a renter in a very expensive area. And so it was also interesting for him to look at that. Data here, we're looking at county level direct estimates. And these are 5-year period estimates. So basically, the American Community Survey, in order to have a large enough sample, is aggregating 5 years worth of data together in a direct estimate to create a period estimate. They won't release the estimates at the 1-year level for every county. So we work instead with 5-year period estimates. And this is from the 2019 American Community Survey. And then our target region here is the South Atlantic Census Division. So it's a group of states in the South Atlantic. It also includes DC. And there's 588 counties in this region. And I'll show maps of this as well. We use covariates in our model, that vector X. And so our covariates are some standard demographic variables like racial and ethnic proportions. And we have some other things that we found helpful as well. So we have the proportion of college graduates in the area. We have the proportion of people in the area that receive some type of public assistance or supplemental nutrition assistance, SNAP. And then we have the proportion of people owning a car and the poverty rate for those areas. So these are covariates, area level covariates that we're using in this analysis. And then lastly, when we fit this model, we're fitting it on the log scale. When we do that, we also have to adjust our variances, and we use the delta method to adjust those survey variances. So this is the analysis we're doing to estimate median household rent burden. And this is what the results look like. So the upper row of plots here are estimates. So the top left is the direct estimates, and the top right is our model-based estimates. And you can see these direct estimates and our model-based estimates generally have the same spatial structure, right? You can see it's higher in South Florida, it's higher in that one region in North Carolina, it's lower in some other regions. You can see that spatial structure, but you'll notice the direct estimates are like a noisy version. The model is able to smooth that noise out, especially in areas where there's a low sample size or a high sample variance. So that's the estimates themselves. And then this bottom row of plots is our log standard errors of our estimates. So again, the left plot here on the bottom corresponds to the direct estimates, and the right plot corresponds to our new SSD estimates. And you'll see generally across the board, the new model reduces the standard error compared to that direct estimate. It should, that's the goal. It's most dramatic in cases where the direct estimate standard error was quite high to begin with. That's really the goal. In areas where we have high standard errors, we want to reduce that standard error, create more reliable estimates. One other interesting comparison here is with that DM, that data Mendel model, which recall that it models inclusion of the random effects, but it doesn't consider any spatial dependence. And so if you fit that DM model on this data set and you just plot the posterior mean of those inclusion probabilities for each area, you get the plot on the left, and you can kind of see some spatial structure there, right? These are quite high in this area down in Florida. They're lower in some areas. You can see spatial structure there, but they're not explicitly modeling that. Our model does explicitly model that dependence. And so if we make the same plot on the right, we see the same general spatial pattern, but a little bit smoother. And that's one reason why we think that our model is able to get more precise estimates than the DM model. And so that was an interesting comparison to make as well. And then a while back, I talked about the E-BLUP of the Fay-Harriott model and how it can be written as the sum of those two terms, the direct estimate, a weighted sum of the direct estimate and the regression estimate. And as the sample variance got small, it gave more weight to the direct estimates. And I said you can assess that visually. And so here we do assess that visually for our SSD model. And so what this plot is the x-axis is the log survey variance, and the y-axis is the ratio of our estimate to the direct estimate. And so you see, as we go towards the left, the survey variance is very small, and that ratio is basically going to 1. So we're basically giving the same weight to that direct estimate as the sample size comes large or the survey variance becomes small. So we're just visually assessing that same property, which is a reassuring property when we look at any small error estimation model. We want to see something like that. So summarize what we did here. So we developed this new small area estimation method. It's an area level method. And it addresses two criticisms. It allows for selection of random effects, which can improve model predictions. And it also incorporates spatial dependence. And specifically, we incorporated spatial dependence at two different levels, at that random effect level and also at the selection process level. We did an empirical simulation study showing that there's potential for this model to outperform existing area level models, right? We saw we can get more precise and accurate point estimates. We can get intervals with smaller width and appropriate coverage. And then we showed how we can use this model to estimate median household rent burden. And we did that for the South Atlantic Census Division. So this was a fairly large data set, at least in the context of small error estimation models. So there's some other things we'd like to do here. We'd really like to scale this up for like truly massive survey data sets. And so one thing we might look into is the use of approximations, specifically variational Bayes, to scale this computation up. So it'd be great to fit a model like this for maybe all of the counties in the entire US, or maybe even go to more granular geographic areas, something like census tracts, of which there's, I think, about 80,000 in the entire US. So scaling things up to that scale would be great. We'd also like to look at this model in the context of other small error estimation goals, things that I talked about earlier, like poverty estimation or health insurance estimation. These are all important topics. And generally, these small error estimation methodologies are kind of general. They can be used for a variety of different applications like that. So we'd like to do that as well. So I'll end there, and thank you.